Okay, problem 3.2 from lecture 3. So this one's two-parted. The first part is actually doesn't involve non-conservative forces, but we're going to do it anyway because it leads on to 3.3, which does. And so it's part one of a two-parted question. And you have a wedge like that. Let's try a bit bigger. This is at, what does it say, 45 degrees, and this is at 30 degrees. And there are two blocks on it, and the blocks are connected by a cable. And let's call that one A, and let's call that one B. Right. The question asks, after these boxes are released from rest, they're not necessarily at the same height, by the way. They don't have to be at the same height. After they're released from rest, and they're going to fall that way, what is the speed of the boxes after they've fallen a meter? Well, I say fallen, this one is going to move a meter downwards, and because they're connected, this will move a meter upwards. So the potential energies of both are changing, and the kinetic energy of both, well, the speed of both will be the same, and because the masses are the same, the kinetic energy of the blocks will be the same. Anyway, tackling this sort of problem, we're going to look for to use our simple expression for conservation of energy, which is at the end of what we introduced in lecture 2, and this is a summary slide. Potential energy plus the kinetic energy is constant, and this is the expression for the potential energy for weight that we'll use. So let's, before I write down that expression for this problem, let's define two states. State 1 at rest, so initial state, and then state 2, which is it's dropped 1 meter. Well, it's slid 1 meter really. And that's where we want to evaluate the kinetic energy. So we have our simple statement of conservation of energy. Potential energy plus kinetic energy at state 1 is equal to the potential energy plus the kinetic energy at state 2. And because it's at rest initially, our kinetic energy is 0. So that's equal to 0. And we can define our datum for each block differently. So, as I say, they're drawn like they're the same level, but they needn't be. But we'll define a datum for each at the centre of mass at state 1. So, in other words, by definition, the potential energy of both boxes are 0 at state 1. And as they climb, this will go up a distance, call it h1, and this is h2. Now, h2 is going to be negative. So when h1 and h2 are 0, so at state 1, then we've got no potential energy. So this tells us then that V2 is equal to minus T2. So now let's think about evaluating the potential energy and the kinetic energy at state 2. So the simplest is probably the kinetic energy. This is what we are trying to find ultimately. So it's half ma, so the first block's mass times v2 squared plus half mb v2 squared, which is equal to, let's go back to the question. Well, they've told us that each box weighs 50 newtons, so the mass is 50 newtons divided by 9.81. So this is going to equal v2 squared. And let me just 50 over 9.81. 5.097 v2 squared. Now we're going to evaluate v2, and that's the potential energy at state 2, and it's got two components because there are two blocks, V2 of block or box A. Did it say where they're boxes? Yeah, they're boxes. And then V2 of box B. And this is where we need just a little bit of trigonometry. If you look at box A, well, it's going to be negative, isn't it? Because H2 is going to be negative. We need an expression for H2. Well, both. So it's going to be MA H2 plus MB H1. H2. That Mg is 50. H2 is minus, because this is negative, and then we've got a 45-degree angle, so it's going to be cos 45, 1 times cos 45, and that get the minus sign there. And then that's right. Now we're doing this one. So MB times G is 50 again. H1 is 1, and this time it's sine 30. So it's 1 times sine 30. It's gone 1 meter along the, that way. 1 meter along the slope. So if you do that sum, well, cos 45, you might remember, is root 2 over 2, and sine 30 is a half, so that's plus 25, which equals, so this is the total potential energy at state 2, minus 50 times square root 2 over 2, plus 25, minus 10.4 Newton meters. Okay, so I hope this is right. Now I've got an expression for V2, which I can put into there, and I've got an expression for T2, which I can put into there. So this tells us that V2 squared is equal to, once you've done the rearrangement, minus 10.4 over, what was this, 5 minus 5.097. So answer divided by 5.097. So 2.03. I forgot to put the negative sign in that calculation if you check. So that means the square root of that gives us the speed. So V2 is equal to 1.43 meters per second. Brilliant. And I hope that's right. So the next part of the question is when it asks us if there's a friction coefficient now, what is the speed? So we'll do that in a moment.